Hi guys, it is Mrs. Allison. Here we go with notes on the idea of definite integrals and then the fundamental theorem of calculus. Here it comes. So we need to first define the idea of a definite integral. And yes, we've looked at integrals before and we talked about them in pretty general terms. Basically that they were the antiderivative of some function. And so that's all we really know. Now let's look at them a little bit more in depth. The difference between a definite integral and the integrals we've looked at so far, what we would call an indefinite integral, is really just one thing, and that's these what we call bounds of integration. Bounds of integration are this b and this a value. Great. Now, with those bounds of integration, it provides a little more context about this integral. What we haven't talked about so far is geometrically what an integral represents. And what an integral represents is an area under a curve. Now, when we say under, it's a little bit misleading, but what it really means is the value of a definite integral can be thought of the signed area. There's a difference between positive and negative, and they matter, the difference matter, between the curve of some function, f of x, and the x-axis. Okay, so just for fun, let's draw some curve that maybe looks like this. I don't know, something like that. And we will call this value here a, and we'll call this value here b. Okay, and so when we talk about the net signed area, we're referring to the amount of area that is positive and negative and then positive again in this case. So for example, I know that this region from A to the point where it crosses the axis, all of this region is positive. So any area that's up here between the curve and the x-axis is represented by a positive value. Let's, for fun, just call this area, I don't know, let's call it 7. And then the area between the curve and the x-axis, but that is below the x-axis, so right here, all of this area will be negative. And so maybe we call this, I don't know, 2. And then again, we see some tiny little area that's still above the x-axis, but not by much, but it too will be a positive number. And so maybe this value is 1. And so what we would say about the integral of this function, the integral from a to b of whatever this function is called, f of x dx, this net signed area is 7 minus 3 plus 2. Oh, wow, that's not a 3. That's a 2. 7 minus 2, and then plus 1. And so if we add those together, 7 minus 2 is 5, plus 1 is 6. So this net signed area here would be 6. Okay, so that is what a definite integral is. It's the area under the curve. Now, we can use our calculators with definite integrals, and really only with definite integrals. We'll talk about some techniques we can use the calculators for integration that are not definite, but for right now we're going to look at the definite integrals in calculators. So I'm going to switch my view just so I can put a calculator up on this screen. So give me just a moment. Okay, we are going to go to our graphing calculator, and we are going to go to the y equals menu. So I'm going to go to y equals, and here I'm going to type in my function, which was x to the third minus 6x. And I'm going to hit graph. Oh, something's not right. Okay, let's try that again. Let's do x to the third minus, gotta go over, 6x. There we go. That will be better. Hit graph. Okay. And I can see on this first example, I want my bounds to go from -3 to 1. And to get the integral, just like it says up above, I'm going to go second, calculate, and I'm going to do number 7. And the lower limit, I'm going to just type in as -3 and hit enter. And my upper limit, I'm going to type in and hit 1 and hit enter. And you can see what it's going to give me is a graph where the shaded regions are highlighted. And so the result that we get this for is the net signed area for that function. So the result of this integral is 4. Okay, looking at the next problem, I'm going to see if I can scoot the camera over so we can see the problem. Looking at this next problem, my bounds go from -√6 to 6. To +√6. Now here's the problem. I know it's the same equation, but if I were to go in without changing my equation, the graph of the shaded region stays. And so it becomes really hard to see what the new shaded region is. So I'm just going to go into my y equals and change something. Let's just retype the -6x, something easy, and hit graph so that it regraphs it so the shaded region goes away. And now what I'm going to do is I'm going to do second calculate, and I'm going to hit the integral, and my lower limit is going to be -√6, √6, hit enter. I could probably close that parenthesis, but I think it'll be fine. And my upper limit is +√6, so I'm going to type in +√6, hit enter. And you can see that the result that we get is 0. Well, let's think about this for a moment. This graph is symmetrical, and we know that the integral is the net signed area, and so it's the area above the curve and below the curve, which means the result should be 0 if it's symmetrical on both sides. All right, so hit pause and try example 3 on your own, or just stay tuned and watch example 3. But as I go through example 3, I do need to change my equation. And I'm going to go ahead and clear that and then go to math. Go over to the absolute value, which is in the number. And I'm going to type in x to the third. I'll make sure I go over this time, -6x. And I'm going to hit graph. We can see the graph looks a little bit different. And I want to calculate the integral with, oops, I hit a different button than I wanted to. Calculate the integral, so second calculate. And I want to go down to number 7, the integral. I want my lower limit to be -5 and my upper limit to be 5. And we get this area that's 198.501. AP wants 3 decimal places, so make sure you include 3 decimal places. Okay, now the next example, example 4, says let's do that from the same thing from the home screen. Well, since I'm using the exact same function, I'm actually just going to leave that in my y1 and recall it. So I'm going to go second quit, and I'm going to go into my math menu, and number 9 is my integral. And the bounds, the nice thing about this format is that it's set up the way the problem looks. So I'm going to go from -5 to 5. And then rather than retyping, although you could, rather than retyping the function in here, I'm just going to choose the variables, go over to y variables, function y1, and then I'm going to tell it to take with respect to x. And then I'm going to hit enter. Now what you should notice is this answer is a little bit different than the last answer. And that's because when it calculates on the graph versus in the main menu, it uses slightly different techniques of calculating, and so the answer is a little bit off. The good news is AP will take both of those answers. Okay, hopefully you had a chance to look at this, and we know that we're trying to find the area between the curves when x is 0 to 2. And so the integral that I would set up, my lower bound would be 0, my upper bound would be 2, and then we'd get 2x squared minus 3x plus 2 dx, and that would be my integral. And if you went ahead and calculated that on your home screen or wherever you calculated that for on your calculator, although I didn't ask you, I just said setup, we would get something like 3.333 is what I got. So hopefully you feel comfortable of understanding what the area under the curve is and what those bounds represent. Because now we're going to move on to what it looks like when it's with respect to y. Okay, like integration with respect to x, integration with respect to y is still a net signed area. And we can integrate with respect to y, which means our bounds are along the y-axis rather than along the x-axis. So if we define an integral this way, the integral would still look the same. It would still say that it's the integral from a to b. This time it would be of f of y dy. Now the difference is that these bounds are y bounds. So that a and that b reference the y value where we're taking our bounds. So when we look at this area under the curve, which is a little bit weird because it's not really under the curve at this point, we have positive and negative regions. So just like before, when I look at this, the positive region would be this region in here that is to the right of the y-axis. So this is positive. And then the areas down here, that was supposed to be blue, the area down here, and the area right here would be negative. So these areas under the curve would be negative at these 2 points. So negative and negative. Okay, so let's look at an example with respect to y, and then talk a little bit about the area under the curve, because sometimes we're not given a function and sometimes we have to actually calculate area. So let's go back to geometry for a little bit. The graph below is a function that is x equals f of y. It's composed of 2 line segments. When they say that, we can trust that they're straight, and a quarter circle. And then it asks us to evaluate each definite integral. And the first one that it gives us is that the bounds go from -2 to -1. Well, if I look at the bounds that go from -2 to -1, I can see this triangle right in here. And this is the area that it's asking me to calculate. I don't know why, sorry, my hand keeps dragging the screen. So this is the area to ask me to calculate. Well, it's an area of a triangle. So do not forget your geometric means of calculating the area of a triangle. This would be 1/2, that's the area of a triangle. Base times height. Well, my base is 1 and my height is 2, or vice versa. And so this area would be 1, except that because it's below the y-axis, and that's the wrong way to say that, because it's underneath the y-axis in the curve, this sign would need to be negative. So we need to be aware, just based on where it's located on the graph, that this would be a negative area under the curve. Okay, let's look at the next one. The next one says, this time I want my area to go from -1 all the way to 2. Okay, well, it told me it's 2 line segments and a quarter circle. So if I separate this, I can see I have a quarter circle right here. And this quarter circle, I might need to think about my area of a circle, but this quarter circle has a radius of 2. And I know that a quarter of a circle times pi r squared, there's my quarter circle, but I'm going to have to add it to the triangle that is also here. And this triangle, like the last triangle that we did, has an area that is 1/2 the base times the height. So 1 times 2. And this area happens to be on the right side of that y-axis, and therefore will be positive. So we know this gives me 1. And over here I've got 4 pi divided by 4, so I've just got pi. So my net signed area under that curve would be 1 plus pi. Okay, well, the next example I want you to try on your own and see what you get. All right, this one asked me to find the whole area, the whole way from -2 all the way to 4. And so the part that I'm missing is this triangle right in here. And this triangle in here is going to be a negative area, so I've got to take that into account. So let's start with that one. That is a triangle that's negative, so it's going to be 1/2 of 2 times 2, so half of 4, which is -2. And then I still have that whole red area that I found before, which we said was pi plus 1. And then I have that whole other blue triangle, which we said had an area of -1. So combining any like terms that I have here, my net result for this area would be pi minus 2. All right, well, let's move on to some properties of definite integrals that we're going to want to know. And there's a couple that stand out in here. One, it says if f is defined at x equals a, then the integral from a to a, meaning my bound starts at a number and ends at the same number, and I'm supposed to find the area under that curve, well, that result's going to be 0 because there is no area. We haven't moved anywhere on the x or y axis, depending on which way we look at it. Okay, so the second one says if f is integrable on the interval from a to b, then if the interval goes from a to b of f of x dx, I actually can rewrite this to say that this, if I want to switch my bounds from b to a, will be the negative. So it's going to be the opposite of the area. That's going to become an important feature for us. We're going to use that pretty regularly, actually. The next properties look familiar because they're very similar to my derivative rules. It says if we have the integral from a to b of f of x plus or minus, it doesn't matter which one, g of x, that I can separate and take two separate integrals. We already looked at this one previously. I also have the property that says that if I have the integral of some constant times a function, I can pull the constant out. Again, we've done that one. And then finally, this one's a little bit weird just based on the order of the letters, but if it says it's integrable on the interval from a to b, and we know that there's a c value somewhere in the middle from a to b, I know it's weird c's in the middle, but if there's some number that's between a and b, then the integral from the low bound to the upper bound of the interval could actually be broken up to say that we want to take the integral from a to c, that point that's somewhere in the middle, and add it to the integral from c to b. And those two integrals are equivalent. That becomes a pretty important property for us, and we will use that pretty regularly. All right, so now we're going to try some examples, but I want you to think about these two problems. They're very similar problems, just slightly different in what they say. So hit pause, and with your seat partner, try example 7 and example 8. Okay, let's look at these. Example 7. First thing we should do is actually understand what this question says. This question says, find the integral from 0 to 5 of f prime of x dx. Okay, what this is actually saying in words, whoa, pencil got fat, hold tight. What this is actually saying in words is, let's find the area under the curve specifically the curve of f prime of x, because that's what's given, from 0 to 5. That's what that statement says. So if we have nothing else, we can find the geometric area under this curve. Well, it just so happens that this curve from 0 to 5 forms a rectangle, and it's going to be pretty easy for us to find the area of that rectangle because this rectangle has a height of 3 and a base of 5, which means that this area under the curve is 15. Okay, well then it asks me to write an equation for the derivative, which is that function that's shown up there. Well, this is a horizontal line, and we know the equation of a horizontal line is just a constant, so this happens to be f prime of x equals 3. And then it asks me to find f of x if f of 1 equals 4. Now, f of x is the antiderivative of f prime. So you guys, this is an IVP problem, meaning we've got an initial value. So what I need to do first is find the antiderivative and then solve for that initial value. So the antiderivative of f prime of x is what I'm asked you to do, or tasking you to do. So this would be the antiderivative of 3 dx. And the antiderivative of 3 dx is equivalent to f of x. So when I take that antiderivative, I get f of x to be 3x plus c. Well, now I need to use that initial value to actually figure out what c is. So I'm going to plug in my 1 and my 4. So we would get 4 equals 3 times 1 plus c. Solving this, we get c to be 1, which means that my function that gave me the derivative of 3 is 3x plus 1 when the initial point is 1, 4. All right, now what I would like you to do is to find the value of f of 5 minus f of 0. Don't want to move too far up, we need f of 5. Well, the value at 5 would be 3 times 5 plus 1, which gives me 16, minus the value at 0, which is 3 times 0 plus 1. Oops, 3 times 0 plus 1. And evaluating that, we get minus 1, and the result is 15. Do you find it curious that this result equaled the area under the curve? Let's keep going. Looking at example 8 rather, the second example like this. Again, we're asking you to find the area under the curve of f prime of x from, this time it's from -2 to 1. And I see that the value at -2 to 1 gives me this rectangular region. And the value from 1 to 2 is this rectangular region. So let's find those two areas, keeping in mind that the area below the curve is going to be negative, where the area above the curve is going to be positive. So starting with that negative area, we would have a -1/2 of 1 times 2. So we get a -1, plus then I need to do the area above the curve, which is going to be 1/2 of 2 times 4, which is just 4. And so this net signed area is 3. All right, let's write an equation for that line. What is the equation for that line? Well, that line, f prime of x, is 2x plus 2. Okay, so let's use an IVP problem again. And this time I want to find when f of 1 is 0. So I know f of x is equivalent to the integral of 2x plus 2 dx. And if I integrate this, I would go up a degree and divide by that degree. But I already had the 2 out front. So that just cancels out. Actually, I'm going to leave it. Plus, go add that x plus c. And here's my function. But I want to evaluate that at my initial value. So I'm going to set up 0 equals 1 squared plus 2 times 1 plus c. Solving this, we get c equals negative 3. So my function is actually x squared plus 2x minus 3. Okay, well, I want you to find f of 1 minus f of negative 2. Well, f of 1 would be 1 squared plus 2 times 1 minus 3. And f of negative 2 would be negative 2 squared plus 2 times negative 2 minus 3. Doing this math, let's see what we get. 1 squared plus 2 is 3, minus 3 is 0, minus, inside here we get 4 minus 4, which is 0, minus 3. So the end result is 3. Here's that curious thing again where the integral was equal to those two numbers. This, my friends, is the fundamental theorem of calculus. Okay, fundamental theorem of calculus, and we're just getting to it? Yep, we are. So, here we go. The fundamental theorem of calculus says this. If f prime of x is continuous, it's a continuous function on the interval from a to b. Then, if I take the integral over that interval that was given of f prime of x dx, that means I'm taking the function f of x, that's the antiderivative of f prime of x, remember, and I'm evaluating it at the lower bound of a and the upper bound of b. So this means right here, this means evaluated from a to b. That's what that phrase means. Then the fundamental theorem of calculus says this, that if I have these bounds and I take the antiderivative of this function f prime of x, then the result is f of b, the upper bound, minus f of a, the lower bound. Well, we just saw that. If I scroll back up here, we just saw that if I take the area under the curve from my lower bound to my upper bound, or I evaluate the antiderivative at my upper bound minus the antiderivative at my lower bound, I get the very same value. Same in both examples. This is the fundamental theorem of calculus. Now, I like this notation, but just so we're clear, it is possible that you see this written slightly differently. Remember, we have that hierarchy that says that capital F is the antiderivative of little f, which is the antiderivative of f prime. So it is very possible that you see this same fundamental theorem of calculus somewhere else, and it looks a little bit different. It may start with an f of x dx in my integral, which means that the fundamental theorem then would be f of b, that's a b, minus capital F of a. So it is possible it looks a little bit different. They say the same thing. All right, let's look at how we use this. This says to evaluate using the fundamental theorem of calculus without using a calculator. All right, here we go. First thing I'm going to do when I'm trying to evaluate an integral is I'm going to rewrite it so that I can actually use it, or so I can take the antiderivative. I'm going to rewrite this to be 2y to the 1/2 plus 1 dy. Okay, now I'm going to take the antiderivative. So I'm going to go up a degree. I'm going to divide by that degree. And then I'm going to make this will be 1y. And I'm evaluating this from 0 to 4. I'm going to clean this up just a little bit. If I do my math correctly, this will be 4/3 y to the 3/2 plus 1y. And again, I'm evaluating it from 0 to 4. So the fundamental theorem of calculus says this. I can take the upper bound, which is 4, and do 4/3 of 4 to the 3/2 plus 1 times 4. Yes, I probably wouldn't write that normally. Minus, and then I'm going to subtract from it the lower bound evaluated. So 4/3 of 0 to the 3/2 plus 1 times 0. I like that second part. That's all zeros. So I'm subtracting 0. Now I need to work some math out. So we've got plus 4, and now I need to do this bit. So 4 to the 3/2 is saying the square root of 4 cubed. Well, the square root of 4 is 2, and 2 cubed is 8. So this gives me 4/3 of 8, or 32/3 plus 4 minus 0. So 32/3 plus 12/3 leaves me with 44/3 is my answer for this one. If we were to check our calculator right now, and we were to do this integral, we should see that the result would be 44/3. Now, it's going to give me a decimal, but it's the same fraction. Okay, you ready for a challenge? Example 10, try it. And you may want to do a u substitution in this. So see what you get. Let's see how you did. If I were to do this problem, and you need a u substitution, which you don't have to use one, I would let u be 4t plus 1. So du equals 4 dt. Well, I don't have that, so I'm going to go ahead and multiply. So I get 1/4 du equals dt. That I do have. So really, this becomes 1/4 the integral of u to the 5th du. If I take the antiderivative of this, I would get 1/4 of u to the 6th over 6. This would normally have a plus c, but we do have bounds on this, so I'm going to go back and substitute in my u. So I get 1 over 24. Instead of u, I'm going to put in what u was, so 4t plus 1 to the 6th. And I'm going to evaluate it from 0 to 1. Okay, here we go. So the fundamental theorem says I'm going to have 1/24 of 4 times 1 plus 1 to the 6th power, I don't know that number, minus 1 over 24, 4 times 0 plus 1 to the 6th power, still 6th power. Okay, so we get, this will end up being 5 to the 6th over 24. Remember, this was a non-calculator question. Minus, well, this would give me 1 to the 6th, which is just 1, so 1/24. Without a calculator, this is as much as I can do. I mean, I probably could figure out what 5 to the 6th is if I spend enough time multiplying. I don't want to. So, how'd we do? That's the fundamental theorem of calculus. Here is another fun type of problem. So if you're feeling adventurous, hit pause, try it, and then come back. Okay, couple things. This gives us some integrals. It says if the area under the curve from 0 to 10 of f of x dx is 17, and the area under the curve from 0 to 8 of f of x dx is 12, find the integral from 8 to 10 of 3 times f of x plus 2 dx. Now, this goes back to those properties a couple pages ago. Specifically, the first thing I want to do is rewrite this integral. So if we take what we're trying to find and I rewrite it, do you agree that I can say that this is equivalent to the integral from 8 to 10? I'm going to go ahead and pull out the 3, the coefficient, of f of x dx plus the integral from 8 to 10 of 2 dx. Okay, looking at this. If we see this integral here, this 8 to 10 of 2 dx, hopefully you think this is the area under the curve of 2, so y equals 2, from 8 to 10. You can visualize that. That's a square. And if you can't, we can use the Fundamental Theorem of Calculus. And here's what that says. The integral of 2 is 2x, and if we evaluate that from 8 to 10, we'd have 2 times 10 minus 2 times 8. 20 minus 16 happens to be 4. Great. So we know that portion is 4. But what about this other part? What about this part that says we want to do the integral from 8 to 10 of f of x dx? We don't even know what f of x is. There's a clue over here. It says that f of x dx equals 17 from 0 to 10, and f of x dx equals 12 from 0 to 8. Well, how is that helpful? Flip back a few pages and look at property number 5. If we look at property number 5, that's exactly what this is. That's what we're going to be using. This says if the integral from 0 to 10 is 17, and the integral from 0 to 8 is 12, then I know what the integral from 8 to 10 has to be. Why do I know that? Well, let's visualize it for just a second. Let's say we have some curve that looks like this, and really I don't know what it looks like, but let's call this 8 and let's call this 10, and then let's draw some curve. Maybe it looks like this. We don't know. But what this says is that the integral from 0 to 10, so this portion right in here, 0 to 10, this integral is 17. Okay, so that area under the curve is 17, total thing. But then it goes on to say that from 0 to 8, this integral, and I'm going to go ahead and color it a different color. We'll color it blue. This area under the curve right there has to be 12. Well, if the whole thing is 17, but just this portion is 12, what does that make the remainder? Well, it makes this difference in here, it has to be 5. So we could say that the area from 8 to 10 of f of x dx has to be 5. So this would be 3 times 5. And 3 times 5 is 15, so 15 plus 4 would be a total of 19. AP loves those type of questions. It's using the properties. You really don't know much else about the function, so you can't use fundamental theorem on everything. And asks you to think about what area under the curve means. All right. Another thing that's important to be able to do with integrals is to look at symmetry. And from what I know, it seems like symmetry is not something we remember all the time. So let's go ahead and review some of our symmetry problems. Okay, if we start with the idea of what it means to be either an odd function, or an even function, that will help define our symmetry a little bit better. If you remember, to be an odd function means that you are symmetrical about the origin. Meaning, if I could stick a pin at the origin and spin my graph 180 degrees, then I'd have the exact same function. So some of the odd functions that we know, some of the easy ones, y equals x. If I graph y equals x, I could rotate it about the origin and it'd be the same graph. Y equals x cubed, same thing. Y equals x to the 5th, x to the 7th, etc. But we also have some trig functions. So for example, y equals sine of x, like we see over here, or y equals the tangent of x. Those are two examples of odd functions, where if I were to be able to stick a pin right at the origin at 0, 0, and I take this curve and I rotate it 180 degrees, I would have the exact same curve. Okay, then we have even symmetry. Well, even symmetry means that your graph is symmetrical about the y-axis. Well, what does that look like? Probably the most common even function that we know is y equals x squared. Y equals x squared, y equals x to the fourth, etc. Another one, a trig function, would be y equals cosine of x. These are symmetrical about the y-axis. Now, why do we go over this? Why is this important? Well, if we can think about symmetry, it can help us find areas under the curve, even if we don't really know or don't have a way to calculate it. With non-calculator questions, if we know symmetry and I know just a little bit about the curve, there's a lot of information I can get from this. So we're going to look at example 12. I'm telling you that the integral from 0 to pi of sine of x dx is 2. It's not quite. This is just an estimate of the area under the curve. We'll call it 2. And I want to use this fact and use the fact that this sine function is symmetrical to find the various areas under the curve. So I'd like you to hit pause and let's start with A through D and we'll come back and check those. Okay, so let's look at this first one. If we know that we're going from pi to 2 pi of sine of x dx, so pi to 2 pi is this other curve back here. Knowing it's symmetrical, knowing what we know about sine, if we say up here that the area is 2 from 0 to pi, so this is positive 2, then we know the area from pi to 2 pi is negative 2. All right, what about from 0 to 2 pi? 0 to 2 pi. What would that be based on the symmetry? Well, it should be 0, right? Because we have a positive 2 above the curve, above the x-axis, and then a negative 2 below the x-axis. Okay, so this next one's a little bit tricky. We're going from pi to pi over 2. And if you go back to your properties, you'll see that this is property number, either number 2 or 3. And if we look at this, there's a problem here. And the problem come with my bounds. Do you notice that my bounds are switched? It no longer goes from low to high. It goes from high to low. And we have a property that says if we need to switch our bounds so that it actually reads from low to high, which is what it should read, then this would actually be the integral from, or the negative, the opposite of the integral from pi over 2 to pi of sine of x dx. And if we look from pi over 2 to pi, given that this is symmetrical, that area would be 1, so this result would be negative 1. So that's a little bit funky with those bounds. Okay, let's look at this fourth example. This is going to be very similar to the example 11 that we just looked at. I'm going to separate this. This really becomes the integral from 0 to pi of 2 dx plus the integral from 0 to pi of sine of x dx. And the area from 0 to pi, area under the curve from 0 to pi of 2, is going to be just 2 pi. If we use the fundamental theorem of calculus, that would say this would be 2x evaluated from 0 to pi. So this would be 2 times pi minus 2 times 0, which would just be 2 pi, plus, and we know that the integral from 0 to pi of sine of x is 2. So this end result would be 2 pi plus 2. All right, let's try the next 4. Hit pause, see what you can do. Okay, coming back to this. 0 to pi of 2 sine of x. This is that first property, maybe second property. Actually, it's not. Fourth property on that list. And this is just a coefficient. So I'm just going to go ahead and pull out my coefficient. So this becomes 2 times the integral from 0 to pi of sine of x dx, which means it would be 2 times 2, or this result would be 4. F. Let's look at example F. What do you remember about your transformations, your function transformations? What do you remember when we have something in the parenthesis in the argument and it's an x minus 2? Hopefully what you remember is that this expression right here shifts my graph right 2 units. But what you should also notice is that these bounds are also shifted right 2 units. So since both my function and my bounds are shifted right, the result of this is the same as the result from 0 to pi. So this result is just 2. Okay, this next one, G. What did you do with G? If we look at G, the problem is this is not sine of x anymore. This has that pi over 2. So what I'm going to do is I'm going to use a u substitution, and I'm going to let u equal x over 2, which means du equals 1/2 dx, which means 2 du equals dx. And so really this becomes the integral. We'll ignore the bounds for just a moment. This becomes 2 times the integral of sine of u du. The problem is, if I were to look at this, this does not match the pattern that we had up top for what it defines sine of x to be. The integral from 0 to pi of sine of x to be. We need to come back to this. So hang tight to this one. We're going to look at it next. All right, what about h? Did you just get 0? Hopefully you just got 0 because we know this is symmetrical from negative pi to pi. So this area will equal this area. And now we'll come back to G because I want to talk about what happens with a u substitution in a definite integral, because we have to deal with those bounds of integration. So there's 2 methods that we can work with to figure this out. The first one is a u substitution that has a bound change. All right, so what does that look like? Well, the idea of a bound change simply means that we, instead of using bounds of x, change them to be bounds of u. Okay, when we look at this integral the way it's written, this says from 0 to 1. Well, what that really means is that x equals 0 and x equals 1. So if we do a u substitution, which this problem needs or benefits from, if we let u equal x squared plus 1, then du equals 2x dx. I don't have a 2x, so I'm going to go ahead and multiply by 1/2 du equals x dx. Now I can make a clean substitution. So we have 1/2 the integral of u cubed du. But herein lies the problem. My bounds were for x. So if I want to do a bound change, I'm going to take my 2 bounds where x equals 0 and x equals 1, and knowing that u equals x squared plus 1, when x equals 1, u is 1 squared plus 1, or 2. So my bound change here will be a 2. And when x was 0, u, if I substitute in u, we would get 0 squared plus 1. So we just get 1. So this bound changes to 1. So changing my bound puts everything in terms of u and nothing in terms of x. So why would we even do this? Well, here's why. If we take this integral now, if we go and define this integral, so the 1/2 was out front, I would go up a degree, divide by that degree. Instead of having to substitute back in my for u, instead of turning this back into x's, since my bounds are already in terms of u, I can just solve from here. So really what I'm doing is I'm taking u to the 4th over 8 and evaluating it from 1 to 2, meaning I would have 2 to the 4th over 8 minus 1 to the 4th over 8. So we'd get 16 over 8 minus 1 over 8, which leaves me with 15 over 8. I don't have to change back in terms of x. Everything can stay in terms of u. So let's look what it looks like if we do a u substitution and then still use the x bounds, meaning we have to substitute back in with x. So let's look at the same problem using method 2. The u substitution, same problem, just different method. If we change back into x, guess what? I'm going to start this problem the exact same way. I notice there needs to be a u substitution, or that's the way I'm going to choose. You can reverse engineer it. We get u equals x squared plus 1. So du equals 2x dx. So 1/2 du equals x dx. And when I go to take the integral, we're doing the integral of 1/2 of u to the third du. But my bounds, remember these are x bounds, we would say x equals 0 and x equals 1. Just so I know I'm not evaluating this yet, because my variables have to be in terms of x's. All of them have to work together. So if I take this integral, I get the same thing. 1/2 times the integral of u to the fourth over 4, evaluated when x equals 0 and x equals 1. And well, in order to use the x equals 0 and x equals 1, this problem needs to be in terms of x. So if I now make my substitution back in, I would have x squared plus 1 to the fourth over 8. And now I'm evaluating it from 0 to 1. These are x's, so I can plug x in for x. And when I do that, I get 1 squared plus 1 to the fourth over 8 minus 0 squared plus 1 to the fourth over 8. And simplifying that, 1 squared is 1 plus 1 is 2. 2 to the fourth is 16 over 8 minus 1 to the fourth, which is just 1 over 8. And I get the same thing I got before, 15 over 8. So really, it's just up to you. Do you want to change the bounds? You don't have to. Okay, I would like you to go back and revisit that problem we looked at on the previous page. Okay, I had to copy and paste it here just for the flow of the video. We got to this point and we said, well, this doesn't work. This is where a bound change comes in. Watch. If knowing that those bounds that we have from 0 to 2 pi are x bounds, if I leave my integral in terms of u and I make a substitution, knowing that u is equal to x over 2, when x is 0, u is equal to 0 over 2. I'm going to put a 0 for my lower bound. And then when u is equal to x over 2 and I use 2 pi, I would get 2 pi over 2, which is equal to 2. And look, this format here now matches, and it doesn't matter that one of the variables is u or du. We just know that the integral from 0 to 2 of sine of some value x, in this case it's u, is 2. So really this problem says 2 times 2, which is 4. So here are two examples to try, and you can try using a bound change. You don't have to. Just see whatever works for you, and then hit pause, and then come back and try them. All right, on this first one, I would let u equal x squared plus 4, du equals 2x dx, so 1/2 du equals x dx. If we look at the integral the way it should be written, it will be 1/2. The integral will come back to the bounds of u1 over the square root of u du. Maybe we even rewrite it just so we're ready to take the integral of u to the negative 1/2 du. Okay, I'm going to choose to do a bound change. You don't have to. Try it a different way if you'd like. But when u is the lower bound at 0, we'd get 0 squared plus 4, which is just 4. And at the upper bound, we'd get root 5 squared plus 4, which is 9. So if we change our bounds, we're going from 4 to 9. So now I'm going to integrate. So I'm going to go up a degree. I'm going to divide by that degree, but I also had that 1/2 out front, so that will cancel. Evaluated from 4 to 9. So really we have the square root of u evaluated from 4 to 9, which means I have the square root of 9 minus the square root of 4, and we get 1. Okay, let's try. This one's a little bit messier. This says the integral from 0 to pi over 6 of 1 plus sine x cos x dx. I'm going to separate this integral. I'm going to rewrite it. I'm going to say this is equivalent to the integral from 0 to pi over 6 of 1 plus the integral from 0 to pi over 6 of sine of x, not dx at that point, sine of x cosine of x dx. Here's where I'd use a u substitution. if we look at this function with a sine of x cos x, I would use a u substitution. I might let u equal sine of x, and the reason I might do that is because when I take my derivative, it's still positive, so du equals cos x dx. And I probably would change my bounds even on this one, just so I don't have to deal with substituting back in, but really, or trig functions, but really it's up to you. If we substitute back in, we would get u equals the sine of 0, and u equals the sine of pi over 6. Sine of pi over 6 is 1/2. So really this portion of my integral is the integral from 0 to 1/2 of u du, which means we'd have u squared over 2 evaluated from 0 to 1/2. I did not leave you enough room here, sorry. 1/2 squared over 2 minus 0 squared over 2. And that gives me 1/8. That result would just be 1/8. Sorry, it's really small. And then if I take the integral from 0 to pi over 6 of 1, really that's just the area under the curve. Or if we want to look at it as antiderivative, it's the antiderivative of x evaluated from 0 to pi over 6. So we would get pi over 6 minus 0. Then I'm going to add to whatever I get on the second half of the integral, which we already know. And so this portion gives me pi over 6. This portion gives me 1/8. So my answer would be pi over 6 plus 1/8 for the area under that curve. All right, finally. Remember how we looked at that question that AP likes where it really doesn't ever define a function? It doesn't tell us what f of x is, it just tells us what it equals, or the integral of that function equals. This is a similar type question. So I would like you to be adventurous. Try hitting pause and try example 15. Just try a couple of them and we'll come back and check. Okay, this first one. This says 0 to 2 of f of 2x dx. I don't have an f of 2x. I don't have that anywhere. So what I'm going to do is I'm going to do a u substitution. So if we let t equal 2x, and the reason I'm choosing t is mostly because all of these variables up here are t. So then dt, the derivative of t, is going to be 2 dx. So the derivative of t is 2 dx. I don't want 2 dx, so I'm just going to solve. I get 1/2 dt equals dx. Just solve for dx. If I do a bound change, when x is 0, t is going to equal 2 times 0. And when x is 2, t is going to be 4. These bounds look a little bit better because I can rewrite this integral now of 1/2 times the integral of a t bound of 0 to 4 of f of t dt. I've made my substitution. I know this. This was given to me. I know that this 0 to 4 of f of t dt is -8. I know that's what that is. It told me. So now I substitute in, and we get 1/2 of -8. And so my end result, or the area under this curve, would be, -4. That would be -4. Great. If you weren't able to get that one first, maybe hit pause now and see if you can get B, and then maybe C as well. All right, here we go. Let's let t equal x over 2. So dt equals 1/2 dx. I don't have a 1/2 in there, so I'm going to reorder this just a little bit. So to get 2 dt equals dx. Using a bound change, because I don't have any integrals that have x over 2 in them, I'm going to change my bounds to t bounds. T is x over 2. When I use that lower bound, that would be 0 over 2, or just 0. And when I use the upper bound, we'd get 2 over 2, which is 1. So I can rewrite this integral to say 2 times the integral from 0 to 1 of f of t dt. I know this. I know this quantity here is 6. So this problem really says 2 times 6. And so this result is 12. Oops, equals 12. All right, finally, try C. If we look at C, and I let t be 2x, then dt equals 2dx. I don't have a 2dx, so I get 1/2 dt equals dx. Using bound change with this u substitution, when t is 1, that lower bound, t is going to be 2 times 1. And when t is the upper bound, it's going to be 2 times 2, which is 4. Okay, so this integral, if I rewrite this integral, this becomes the integral of 1/2 the integral from 2 to 4 of f of t dt. Great. But it's a bit problematic. Why? I don't have an integral from 2 to 4. I have an integral from 0 to 2 and 0 to 4. So can I use my properties to be able to come up with that integral? Hopefully what you think, and maybe we wouldn't write this necessarily, but hopefully what you realize is that this integral here can be rewritten to be the integral from 0 to 4 of f of t dt minus the integral from 0 to 2 of f of t dt. Just like we looked at before, we don't really know what this curve entails. We know from 0 to 1 is 6, we know from 0 to 2 is 4, and we know from 0 to 4 it's -8. So maybe this curve looks something like this. So here are my x values that I know. I know from 0 to 1, I know from 0 to 2, and then I know from 0 to 4. Okay, so from 0 to 1, it's 6. 0 to 1, it's 6 total units, whatever that looks like. And then by the time I get to 2, I'm only at 4. So that means, oops, I didn't draw that very well. So that means that from here down to here, that this total area, if this is 6, by the time I get to 2, I'm only at 4. It means that this quantity right here needs to be -2. It needs to just be 2, the area under the curve, but because it's below the x-axis, it's -2. So that by the time I get to 2, I only have a unit 4. Well, then it keeps going. And then it says, by the time I get all the way to 4 on the x-axis, I'm all the way at -8. Okay, so what does that look like? Well, that looks like that if I were to add up the two areas that we know this much plus this much right here is a total of 4. So we can say that the area of 4 plus some unknown quantity over here, we don't really know what's happening just yet, but by the time I add that x value, I know that the end result should be at -8. Okay, because what I'm trying to figure out is what happens from 2 to 4. Well, if I solve this for that purple region, we get that x equals -12. So I could show my work that way and know that this end result right here is -12, and then I have to take half of it. Or we know that from 0 to 4, this is -8, and then from 0 to 2, it's 4, but I'm subtracting it. That also gives me -12. There's lots of ways to think about these problems. So I'm doing half of -12. Oh my goodness, what am I writing? Half of -12, which is just -6. And so that end result would be -6. So lots of fun ways that we can use that fundamental theorem of calculus.